Welcome to AlibreCAM, brought to you by MecSoft Corporation. Today we'll be introducing 2.5 axis milling. To launch the AlibreCAM mill module, select the Add-ons tab from the ribbon bar. You will observe an entry called AlibreCAM. Select the mill entry, and this will display the AlibreCAM browser as a separate tab next to the Design Explorer tab. Before starting any new CAM project, you should first perform the following startup checklist. For more detail on each of these items, you can refer to the 3-axis introduction companion video. We will perform the following basic steps in machining this model. First, we will define the machine and the post-processor to use. Then, we'll define the machine setup, including the stock geometry, material, and work 0. Then, we'll load a predefined tool library. Then we'll create predefined machining regions on our part. We will generate our 2 1/2 axis toolpaths, including a facing operation, 2 pocketing operations, and a profiling operation, using predefined regions. Then we'll simulate and post-process the toolpaths. Now, before we begin, I want to mention the layout of the Program tab. You will notice that we will progress from left to right. We'll start with setting the machine, then the post, setup, stock, alignment, material, and then the work 0. Only after those steps are completed do we create machining operations. Let's start by defining the machine and the machine tool coordinate system to use for this job. From the Program tab, select Machine to display the dialog. Under the Machine Tool Coordinate System tab, select the World Coordinate System button. By default, the MCS, or Machine Coordinate System, is already aligned with the WCS, or World Coordinate System, so this step is not required for this part. Now select the Machine Tool Definition tab. Under Machine Type, set the number of axes to 3 axis. This is the correct selection for both 2-axis and 3-axis operations. Pick OK, and notice that the machine type now appears under the machining job in the machining browser. Next, we'll define the post processor. From the Program tab, select Post to display the dialog. For the current post processor, select HOS from the list of available posts. Then set the posted file extension to NC. Other file extensions are available depending on your machine requirements. Pick OK, and notice that the post type now appears under the machining job in the machining browser. Now, let's define the machining setup. If there is no setup one listed under your machining job, the system automatically creates one when a work 0 or an operation is generated. However, by default, the MCS, or Machine Coordinate System, is already aligned with the WCS, World Coordinate System, so this step is not required for this part. However, in production, you can have multiple setups and assign different machining orientations for each. In this step, we'll define the raw stock from which to cut the part. From the Program tab, select Stock, and then select Box Stock from the menu to display the dialog. First, we'll select Copy Bounding Box. The system analyzes the part and displays the maximum dimensions of the part. Then, we'll set the height to 2.5 and leave the length and width set to the computed part boundaries. Note that the stock dimensions you enter here are measured from the corner of the bounding box selected in this dialog. Pick OK, and notice that the stock type now appears under the machining job in the machining browser. If the stock does not display on the screen, select the Stock Visibility icon located at the base of the machining browser. With the stock displayed, we can see that the height of the stock leaves extra room to cut the part in the Z-axis. Once the stock model is created, you can move it in alignment with the part if needed. From the Program tab, select Align to display the dialog. Since we'll be removing material from the top of our part, we want to align the stock flush to the bottom of the part. So for Z alignment, we select bottom, and for XY alignment, we select center, and then pick OK. The stock is now aligned flush to the bottom of the part in the Z-axis and centered in the X and Y axis. Next, we'll set the material for the stock geometry. From the Program tab, select Material to display the dialog. For Material, select Aluminum 6061 from the list of available materials and then pick OK. The material texture is displayed in the stock simulation window. Select the Simulate tab and then pick Window to open the stock simulation window. If the material texture does not display on the stock, select the Material Texture Visibility icon located at the base of the machining browser. Material texture is only for display purposes, and for this part, we will leave it toggled off. Now select the window icon again to close the stock simulation window. Now that the stock is aligned to the part geometry, in this step we will establish the work coordinate origin. This location defines the 0 point from which all toolpath points are interpreted by the controller. From the Program tab, select Work 0 to display the dialog. Then select Set to Stock Box. Then set 0 face to highest Z and 0 position to southwest corner. This sets the machine home to the top of the stock material and the southwest corner of the stock geometry. Pick Generate and notice that the MCS is translated and that the Work 0 now appears under Setup 1 in the machining browser. To save time, we will load a predefined tool library. Next to the Program tab at the top of the machining browser, locate and select the Tools Machining Objects button. Selecting this button toggles the machining object's lower portion of the browser on and off. From the Tools tab in the Machining Objects browser, select Load Tool Library to display the File Open dialog. Select the predefined tool library file named 2-axis introduction tutorial.vkb and then pick Open. The message says that 2 tools were added, and we see that a 3/4 inch flat mill and a 1/4 inch flat mill appear in the Machining Objects browser. If you double-click on one of the tools, you see it displays the Create Edit Tools dialog with its dimensions and speeds and feeds parameters already defined. We will be using the 3/4 inch flat mill for our facing and pocketing operations, and the 1/4 inch flat mill for our profiling operation. To save time, you can create predefined machining regions on your part and then use them as needed when creating your machining operations. For this part, we will create 1 predefined region for our facing operation and 2 predefined regions for our 2 pocketing operations. From the Machining Objects browser, select the Regions tab and then pick the Flat Area Selection Filters icon to display the dialog. Check the box next to Ignore All Inner Regions and uncheck all the other options. When checked, only the outer region of a selected flat area will be defined by the region. Now pick OK to continue. Now pick the Select Flat Areas icon. We will now pick the top face of the part, and then pressing Enter or selecting the checkmark icon will accept the selection. This creates a flat area region around the top outside edge of the part. Because we checked the box to ignore all inner regions, only the outer profile was used, and that's what we want. In the Machining Objects browser, you see that a new machining region set was created automatically, and that Flat Area Region 1 was created, added to the set, and then selected. It is also highlighted on the part. Now we'll create another region. Pick the Select Flat Areas icon again. This time, select the pocket face that resides just below the top face, as shown here, and then pressing Enter or selecting the checkmark icon will accept the selection. This creates a second region, and you see that Flat Area Region 2 was created and added just below Flat Area Region 1. It is also highlighted and selected. Now, for the third region, we want to change our selection filter. Pick the Flat Area Selection Filters icon again. From the dialog, uncheck Ignore All Inner Regions, and then check the box next to Ignore Outermost Region, and then pick OK. As the filter suggests, this will ignore the outermost region on the selected flat area. Now, pick the Select Flat Areas icon again, and then select the same face we picked last time, and then pressing Enter or selecting the checkmark icon will accept the selection. You see that with the selection filter changed, selecting the same face creates a region that ignores the outer profile. We see that Flat Area Region 3 was created and added to the set. Now if you select each flat area region from the set, each will highlight on the part. You should note that the actual number value at the end of each region automatically increases incrementally depending on your currently active session, so the numbers you see may differ. With our flat area regions created, we can move on to create our facing and pocketing operations. Now change back to the Tools tab. Now we're ready to create our 2 1/2 axis facing operation. From the Program tab, select 2 axis and then Facing from the menu of 2 axis operations. This will display the 2 1/2 axis facing operations dialog. By default, the Control Geometry tab is displayed first, allowing you to define part and/or avoid regions. We'll select the Part Regions tab because we want to contain the facing toolpath to the top profile of the part. To save time, in this part, we have already predefined several machining regions. To select one of our predefined regions, we pick the Select Predefined button from the dialog. This displays the Select Predefined Machining Regions dialog. You can see that under the Machining Regions folder, we have one machining region set that contains 3 flat area regions. Selecting a region from the tree will highlight it on the graphic screen. For our facing operation, we want Flat Area Region 1, so we will select it and pick OK. We see that Flat Area Region 1 was added to the Drive Region section of the Control Geometry tab. Now we switch to the Tool tab of the dialog and select the Flat Mill 3/4 inch tool from the list of available tools. Note that the tool parameters of the currently active tool are always displayed in the status bar at the bottom of the Machining Objects browser. Now switch to the Feeds and Speeds tab. Then pick the Load From Tool button. The system will retrieve the feeds and speeds parameters that were set when the tool was created and associate them with the current operation. Next, we'll switch to the Clearance Plane tab. Set the clearance plane definition to Automatic and the Cut Transfer method to Clearance Plane. In the automatic mode, the system will determine a safe height for locating the clearance plane. Setting Cut Transfer to Clearance Plane will force all transfer moves to be performed in this computed clearance plane. When this dialog is active, the clearance plane is shown on the graphic screen. Now switch to the Roughing tab to control the cutting. We'll set the tolerance to 0.001 and set the stock to 0. We will not be leaving any stock material left on the part after machining. Now we'll select Island Offset Cuts as the cutting method. This means that the tool will move in successive uniform offsets of the part shape. For the cut direction, we'll select Mixed. The system will determine a mixture of both climb and conventional cutting. For the step-over distance, which is the distance the tool will move per pass in the X and the Y, we'll make it 30% of the tool diameter. In the future, you can also specify the step-over by entering exact linear distance. Now we select the Cut Levels tab, and for the location of cut geometry, we'll select At Bottom. Even though this is the top of our part, it represents the bottom of our actual cutting depth. You can refer to the images in the dialog for information about what each parameter means. Under the Cut Depth Control section, we'll set the total cut depth to 0.25. This will get down to the actual top of our part. Now you will see 2 fields below this, one called Rough Depth and the other called Finish Depth, and then also a slider. These values allow you to split your total cut depth into a rough and a finished depth. The slider allows you to adjust the two values together. If you click on the slider, you see that the rough depth will automatically set to the total cut depth we entered. If you move the slider, you see that it can be used to automatically split the rough and finished depth values. You can, of course, override the slider by entering values directly into the fields provided. These additional two sliders below it allow you to control the depth per cut for both the rough and the finished depths. Together, these parameters and sliders offer precise control over your cut levels. For this operation, we want just one pass, so we will set the total cut depth and the rough depth per cut each to 0.25. Under Cut Levels Ordering, we'll select Depth first. Again, the images on each tab of the dialog help explain what each parameter means. Now we'll pick Generate to calculate the toolpath and display it on the graphic screen. Note that the display of the toolpath in the graphic screen can be turned on and off by selecting the toolpath visibility icon located at the base of the machining browser. The new toolpath can now be simulated to display the in-process stock model. Switch to the Simulate tab at the top of the machining browser, and then pick the window icon to open the stock simulation window. Select Preferences and set the simulation model to polygonal and the simulation accuracy to fine, and then pick OK. Under Preferences, uncheck Simulate by Moves and adjust the slider to set the simulation speed. Now select the 2 1/2 axis facing operation you just created and then pick Play to run the simulation. If you don't want to wait for the entire toolpath, you can select Pause and then To End to calculate and display the entire toolpath simulation. Then we can select the toolpath visibility icon from the base of the machining browser to turn off the toolpath and see the in-process stock model. Now select the window icon again to close the stock simulation window. With the facing operation complete, we will now program our two pocketing operations. In 2 1/2 axis pocketing, geometry regions on your part are used to control the X and Y extents of the toolpath, and all sidewalls are considered vertical. You need to understand that if the sidewalls on your part are tapered, you may need to use 3-axis operations instead. From the Program tab, select 2-axis and then Pocketing from the menu of 2-axis operations. This will display the 2 1/2 axis pocketing operations dialog. From the Control Geometry tab, select the Part Regions tab and then pick the Select Predefined Regions button. We will select Flat Area Region 2 for the first pocket, and then we'll pick OK to continue. We see that Flat Area Region 2 was added to the Drive Regions section of the Control Geometry tab. Next we'll go to the Tool tab and again select the Flat Mill 3/4 inch tool from the list. Next we'll select the Cut Parameters tab and set the tolerance to 0.001 and the stock to 0. Cutting the pocket to its finished length and width. For the cut pattern, we'll select Offset. This will create a toolpath with successive offsets of the control geometry. For climb direction, we'll select Mixed, and for start point, we'll select Inside. For the step over distance, we'll make it 50% of the tool diameter. With the offset cut pattern, you have this additional option called Clean Corners, and we'll check it. The system will automatically detect if there were any corners in the pocket that the tool could not reach between passes, and if so, it will create an additional pass to clean them up. For the Cut Levels tab, we'll set Location of Cut Geometry to At Bottom, because our predefined region is located at the actual bottom floor of the pocket. Similar to our facing operation, we'll set the total cut depth, rough depth, and rough depth per cut to 0.25 and then pick Generate. The 2 1/2 axis pocketing operation is then displayed. The new toolpath can now be simulated. switch to the Simulate tab and open the stock simulation window. Then select the 2 1/2 axis pocketing operation we just created and then pick Play to see the in-process stock model. Now we'll turn our attention to machining our second pocket. Switch to the Program tab in the machining browser. Select the 2 1/2 axis pocket operation we just created. Right-click on the selected operation and select Copy. Now right-click again and select Paste. This creates a copy of the operation and places it below the original in the machining browser. Now right-click on the second operation and pick Edit to adjust its parameters. First, we'll pick Remove All under the Control Geometry tab. With Drive Region selected from the Control Geometry tab, pick the Select Predefined button. For this pocket, we will select Flat Area Region 3 and then pick OK to continue. We see that Flat Area Region 3 was added to the Drive Region section of the Control Geometry tab. If you look at the part, you will see that this pocket contains an island in the center. We want to include this as an additional drive region. To do this, we will pick the Select Flat Area Drive Regions button. The dialog minimize and will select the flat face at the top of the island, and then pressing Enter or selecting the checkmark icon will accept the selection. You will now see that a second region was added to the Select Machining Regions list in the dialog. If you select each region from the list, you will see that the first represents the top outer profile of the pocket, and the second represents the top outer boundary of the island. Next we go to the Tool tab, and again we'll pick the Flat Mill 3/4 inch tool from the list. Next we'll switch to the Cut Parameters tab, and we'll set the stock to 0.025. In 2 1/2 axis pocketing, stock only refers to the material that is left on the sidewalls. Setting the stock value to 0.025 will leave 25 thousandths of stock material around the sidewalls of the pocket and the island, which can then be finished using the profiling operation. We'll leave the remaining settings on this tab to match our first pocket. Now we'll switch to the Cut Levels tab. We mentioned that the stock value on the Cut Parameters tab applies to the sidewalls of the pocket. The Cut Levels tab applies to the Z-level cutting and the floor of the pocket. We'll start by setting the location of cut geometry to At Top. This is because the predefined region we selected represents the top of our pocket. For the total cut depth, we will select the Pick button. The dialog minimizes and allows us to select 2 points to define the total cut depth. Now we'll select 2 endpoints. The first endpoint can be anywhere on the top perimeter of the pocket, and the second endpoint can be anywhere on the bottom perimeter of the pocket. It doesn't matter which endpoints you select on the top and bottom perimeter because the system will calculate the depth for you, as long as one is on the top and one is on the bottom. The dialog reappears and we see that the total cut depth was calculated as 1.75. Next, we'll set the rough depth per cut to 0.25. Each pass will remove 1/4 inch of material. We want to make sure that the checkbox for Clear Island Tops is checked. This will make sure a cleanup pass is added at the top of the island, since its height is different than the top face of the pocket. Let's take a moment to review the cut depth control parameters. You should have the total cut depth set to 1.75. The rough depth set also to 1.75. The finish depth is set to 0. The rough depth per cut is set to 0.25. And the finish depth per cut is set to 0. Now we pick Generate. Once the toolpath is calculated, we'll make sure that the display of the toolpath is toggled on, and then we'll select the Display Toolpath and Levels icon from the base of the machining browser. This will allow us to see each level in the toolpath individually. As you can see, a cut level was located at the top of the island, just like we wanted. Now close the Z-level display dialog. The new toolpath can now be simulated. Switch to the Simulate tab and open the stock simulation window. Then select the 2 1/2 axis pocketing operation we just created and then pick Play to see the in-process stock model. For our final toolpath, we'll add a 2 1/2 axis profiling operation as a finishing pass to clean up the sidewalls of the larger pocket. From the Program tab, select 2 axis and then Profiling from the menu of 2 axis operations. This will display the 2 1/2 axis profiling operations dialog. For this operation, we want the bottom of the pocket to drive the toolpath. To do this, we make sure the Drive Regions tab is active and then pick the Select Flat Area Drive Regions button. The dialog minimizes and will select the flat face at the bottom floor of the pocket, and then pressing Enter or selecting the checkmark icon will accept the selection. The dialog reappears with the Drive Flat Area 1 added to the list. Next we'll go to the Tools tab and this time select the Flat Mill 1/4 inch tool from the list. Next we'll select the Cut Parameters tab. From here we'll set the tolerance to 0.001, the stock to 0, and we'll set the cut direction to climb. Then for Cut Start Side, we'll check the box next to Determine using 3D Model. The system will then determine which side needs to be cut based on the 3D model of the pocket and the island. We need no step-over control since it is only making one pass. Then, on the Cut Levels tab, the location of cut geometry is set to At Bottom, and we can then pick Generate. Now select the Toolpath Visibility icon at the base of the machining browser to have a look at the new profiling toolpath. The new toolpath can now be simulated. Switch to the Simulate tab and open the stock simulation window, and then pick Play to see the in-process stock model. To see all of our toolpaths simulated together, select Setup 1 and then pick Play. Now, with the toolpaths complete, we're ready to post-process to an output text file containing G-codes that can then be sent to the machine tool to actually machine the part. Select Setup 1 from the machining browser and right-click and select Post. This will post all operations created under the setup. By default, the part file name and the setup name are appended for the G-code file name. Also by default, the posted G-code file is saved to the folder where the part file is located. Now pick Post and the G-code file is displayed in Notepad where it can be viewed or edited manually. This completes our introduction to 2 1/2 axis milling with the AlibreCAM, brought to you by MecSoft Corporation. For further assistance, you can visit the online help supplied with the program or visit www.mecsoft.com for additional tutorials. Thank you.